Welcome to today's panel discussion on syntactic foams research and applications, an update from Europe. I'm Nikhil Gupta. I'm a professor of mechanical and aerospace engineering at New York University and host of this event. We want to acknowledge the US aid funding to make these events possible. This virtual panel discussion series is trying to capture the research and development efforts in syntactic foams from around the world. The first panel discussion took place on December 4th, and the second one was organized on January 14th. The recording of these panels are available on YouTube. We'll post the YouTube links in the chat. These panels are an opportunity to directly ask questions from some of the leading experts in syntactic foam field. So we hope this information that emerges from these events can guide some of the future research efforts in syntactic foams area and make research relevant to the needs of the industry. Today, we are fortunate to have three eminent panelists with us. They need no introduction in the syntactic foam community, so I'll keep their introduction brief from my side. Our first panelist, Professor Will Parnell, is a professor of applied mathematics at the University of Manchester and leads the mathematics of waves and materials research group. He is the editor-in-chief of the international journal Wave Motion. He works on the development of new models to understand the deformation of complex materials and wave propagation in such media, including metamaterials. His PhD focused on homogenization models for syntactic foams. Throughout his career, he has been interested in understanding the nonlinear behavior and the associated elastodynamic response of polymer metric syntactic foams. Our second panelist, Dr. Georg Weise, is from Germany. He studied physics at the Technical University of Chemnitz, followed by his PhD in material science at the University of Mining and Technology at Freiburg. At Fraunhofer IFAM, he has been a project manager in the departments of casting and powder technology with special interest in metal foams. His research with syntactic foams started in 2006 with cast aluminum and zinc matrix foams. This was later complemented by sintered iron alloy and composite syntactic foams. Our third panelist, Professor Lorenzo Bardella, is from Italy. He is an associate professor of solid and structural mechanics in the Department of Civil, Environmental, Architecture, Engineering, and Mathematics at the University of Brescia. He received his PhD in 2001 for materials for engineering from the University of Brescia. His dissertation focused on micromechanics of glass epoxy syntactic foams. In 2009, he was recipient of the first junior prize in mechanics of solids awarded by the Italian Association for Theoretical and Applied Mechanics. With emphasis on modeling, Professor Bardella's field of interest includes small-scale particle behavior of metals and mechanics of composite materials and structures, and the actuation and sensing of elastoactive materials. I'm pleased to welcome all our panelists. Now I request each panelist to take about 5 minutes to give an overview of their work related to syntactic foams. Attendees can ask questions using question answer utility, and we'll take some questions as we go. So let us start with Professor Parnell, and I'll let you share your screen.
Okay. So hopefully that's visible.
Yes, it's visible. You can put it in the full screen mode. Yeah, thank you.
Yeah, okay. Excellent. Okay, so thanks to Professor Gupta and to Gary for organizing today's sessions and all the previous sessions. As I said earlier, I couldn't make the one in January due to the time difference, but it's great to connect these communities. So I work in mathematics at the University of Manchester. I've been here for about 20 years now, in fact. Things have changed an awful lot during that time, but our research group in Manchester, as Professor Gupta has said, is mainly focused on mathematical modeling, and in particular how mathematical modeling enables us to understand wave propagation in complex materials and a variety of metamaterials as well. So this is a sort of broad overview of the research that we do. So obviously syntactic foams is a key part of that, but we do lots of other types of research associated with soft biological materials, in particular those under large deformation. We work on fundamental scattering associated with wave propagation and diffraction from edges and corners. We do models from homogenization and multiple scattering in order to understand propagation in very complex microstructured medium, including syntactic foams, of course. And we also think about new metamaterials associated with usually acoustics and elastodynamics. So this is our normal home. So this is the Alan Turing building in Manchester. The sky isn't always blue, but it often is. And I think it was actually when Professor Gupta visited at the end of 2019, we held a very nice workshop, just 2 days, quite a small focus workshop associated with syntactic foams in Manchester. It was the good old days where people could actually get together and talk about science in person. But it's fantastic that we've got this opportunity to do this virtually. And strangely, I think it's quite useful to be able to do this virtually. It connects more people than we could do, for example, at the small workshop in Manchester. So our main interest in terms of syntactic foams is all polymer syntactic foams. In fact, so when microspheres are these expansile thermoplastic microspheres, we try to couple mathematical models of nonlinear behavior with experiments, and we're critically interested in nonlinear constitutive behavior, viscoelastic response, and the acoustic response. And so we're interested in being able to model this kind of complex nonlinear behavior that arises in these syntactic foams, usually associated with the complex buckling and interaction of the microspheres within the composite material. So with added filler, you obviously get this increased stiffness initially, but obviously this softness at large strains. These materials are, however, very, very good in terms of their recoverability. So that's a key advantage of them over things like glass microspheres. We've done quite a lot recently in terms of materials characterization. So we've got very good X-ray computed tomography machines at Manchester. And so we're able to do things like characterize microstructure, radius distribution, etc., and also imperfections and defects within these kinds of materials. And finally, recently, we've done quite a lot in terms of nanoscale resolution and characterization, mainly to try to understand shell thickness distribution and a bit more information about these kinds of expansile microspheres. And we've tried to couple those to models, not for the prediction of the mechanical properties of the medium, but more in terms of the prediction of the shell properties themselves. So thanks again for organizing this, and I look forward to the discussions.
Thank you very much. George, do you want to go next?
At the moment, I'm not allowed to show slides.
Oh, okay, let me check again.
Yeah.
You have the co-host permissions to share slide.
No. Okay.
Yeah.
You see it?
Yes.
Okay. Yeah. Thank you. So my name is Joerg Weise. I'm working in the Department of Powder Technology at the Fraunhofer Institute IFAM here in Bremen. You see the university campus in this picture and the building on the right. The institute is more than 50 years old. We have now more than 700 employees working in 20 departments. And as you can see in the following slide, which shows the core competencies of the Institute IFAM, we work in a very wide field of research. So we work on surface technology, adhesive bonding, fiber reinforced materials. And the part I work in is related to casting of metal melts, powder technology, and electrical components and systems. So it's a very wide field of research interest in our institute. We work more application related, I have to say, in comparison to universities. This is a Fraunhofer model. So we are not working that much in fundamental research. So we are situated somewhere between industry and fundamental research. In relation to porous metals and metal foams, our activities started more than 20 years ago, actually. No, 30 years, sorry, more than 30 years ago, with the development of Fominal, one of the metal foams which was really, or which is really applied in the industry. So you can see on the top left. And the second variant of this foam type is the aluminum foam sandwich. This is also produced in serial production. And the third variant of this aluminum foam is the so-called APM spheres. You can see there. This is still not in production, but we have a lot of interesting projects with the industry. Porous materials not only produced by classical foaming, but also by other techniques like, for instance, additive manufacturing, or like casting. In the middle, you see one example of an open porous aluminum foam, which was produced by means of infiltration of placeholder structures with aluminum melts. Okay, on the right side, you see some examples of, in this case, cast syntactic foams. I will show some examples later. And when you look at the bottom, we are also working on sintered fiber structures. In this case, it's hollow fibers, hollow copper fibers sintered to a heat exchanger structure. Also other sintered open porous foams, open porous magnesium foam in the middle. And we recently started also to look on nano porous metals developed or produced by means of de-alloying. And coming to the syntactic foams, we started a bit later in 2004. I was still in the casting department, so we started with casting production of syntactic foams with aluminum and zinc. We also tried to combine it, or we combined it with other kind of foams. In the middle top, you see one example of a syntactic foam combined with a ceramic foam. Syntactic foams are mostly known to be closed porous, but with some special treatments, you can open the structure. You can see on the right side on top. So two sintered spheres, or the sintering neck of two hollow spheres. And the hollow sphere structure was later infiltrated with metal, and the sintering neck was then later opened using a high pressure treatment with water. We combined such open porous zeolites also with active materials, like for instance zeolites. And coming to the sintered structures, we later changed to combine the hollow spheres also with steel or iron or other sinterable metals. So one focus in our department is in metal powder injection molding. So in this, with this method, you can produce near net shape components made with the hollow spheres. You can also use feedstock extrusion. It's almost the same process, but resulting in other geometries. And those techniques we used for iron combined with nickel, copper, chromium, hyalite steels, and so on. And using injection molding, you can also combine nicely the foam with compact material. As we see from our activities with foams, it's all the time used in combination with compact material. So here you can do this in one process. And one of the more recent activities was the adaptation of the properties by means of hardening of steel, syntactic steel foam. Okay, that's all I wanted to show.
Thank you very much. Lorenzo, floor is all yours.
Sure. Let me share the screen. Can you see it?
Yes. Yeah,
Okay.
it's showing up.
First of all, thank you very much, Nikhil, for organizing this. I'm going to very briefly summarize the models I've contributed to develop in more than 20 years. And this has been possible thanks to the collaboration with several colleagues and students who are listed here. And I apologize to those who I forgot, if any. I work in Italy, which is a country facing on the Mediterranean Sea, South Europe, and Brescia is in Lombardy, which is a north region of Italy. And here you see the region. We are 19 kilometers east to Milano, and we are close to the Alps and in between two nice lakes. Here you see a partial view of the engineering campus. Here, top on the right, the entrance of the department where I work in Brescia. And here, one of the picture of one of the main squares in the city center. As far as I know, here in Brescia, research on synthetic foams started in the mid-90s within a material science lab where they produced, characterized, tested glass epoxy systems. And so I joined when I had to start my master thesis. And so I did myself some experiments. I took these pictures myself and I produced this sample, for instance. And however, my task was to do some modeling. And so here in Brescia, we have developed models, micromechanical models, from which we want to understand something of the composite behavior, starting from the knowledge of the behavior of the phases, of the single phases. So matrix and balloons in the case of synthetic foams. So we developed analytical homogenization, and within this micromechanics framework, we developed analytical homogenization and finite element models of the synthetic foams microstructures from which we want to understand something of the behavior of these materials. About analytical homogenization, we started by developing linear elastic homogenization procedures to have accurate estimates of the effective elastic moduli. Then we got a grant from Intermarine, which is a big Italian company. It is a shipyard, a big shipyard company in Italy. And so we developed an analytical procedure to optimize the mechanical response of sandwich panels, of glass epoxy sandwich panels whose core is in synthetic foam. And finally, we extended the linear elastic homogenization procedure to the nonlinear range in a so-called modified second method. About computational micromechanics, that is finite element models, we started by studying the effect of the nonlinear viscoelasticity of the epoxy matrix on the overall behavior. For this purpose, we used a simple unit cell model and we studied the cyclic behavior of various foams by using this constitutive law for the epoxy resins. And then we developed a sort of nonlinear Eshelby-like model, which was used to provide an explanation for the brittle fracture of a specific syntactic foam under uniaxial compression. Later, we started working with NYU, so with Nikhil, Gupta, Maurizio Porfiri, and their students. And we started developing multi-particle unit cells. And first, we used these multi-particle unit cells to critically assess the linear elastic homogenization procedures we developed. And then we used these models to understand something of the brittle failure under compression by plugging into these models a novel criterion for the failure of the microballoons. And then what we did, we extended these models by different nonlinear inelastic constitutive models for the matrix to understand some other behaviors like the ten swing from high strain rate. And the last model we worked with was in collaboration still with NYU, but also Noël Tessier from CMT Materials of Massachusetts. CMT supported, by the way, the study of the student mailing involved in this research. And here, we developed this quite complex micromechanical model whose purpose was understanding the different failure modalities of syntactic foams under hydrostatic pressure and different failure modalities dependent on whether the samples are painted or not. And let me remark that this model is quite interesting because here the filler volume fraction is 69%, which is quite a large amount for a computational model. I think that's it. Thank you.
Thank you very much. So that was a good introduction from everybody. I'll start with the first question that we are representing different parts of Europe, Italy, Germany, and England. So who's funding the syntactic foam research in these countries? Is it industry? Is it government organizations? And what is the mechanism? How the support has been so far?
Yeah. Okay, if I may start.
Sure.
The syntactic foams is a very interesting field for me, but in respect of funding, it's not the best field, I have to say. Especially at the moment, we had a little bit of funding from government a few years ago, but at the moment it's really difficult to get funding for such a lightweight subject. So you have to combine it with some terms like digital, additive, artificial intelligence, and so on. Otherwise, you have no chance to get any funding. Yeah, we have some interest in industry, but it's not large projects, I have to say. Yeah, but there is interest.
Lorenzo, have you seen support in Italy for lightweight materials in general, maybe syntactic foams in particular?
I'm a theoretical guy, so I don't need too much funds to do my job. But beside supporting students, which is anyway a key issue. So I know that when I was a PhD student, we got funds from this company I mentioned in my little presentation, which is Intermarine, and it is, as I said, shipyard company, and it was quite a big project, and there were also Polytechnic of Milan involved in that project, and I was a PhD student, so my advisor looked for those funds, and so this was the only experience I had about getting funds from Italian companies. Otherwise, as you well know, we got support from CMT Materials from Massachusetts to do this research on syntactic foam for deep buoyancy applications, and so this is what I know. I think that one important issue that usually companies don't know, if you look for funds, is that sometimes they can deduct much of what they give to the university from taxes. So usually they don't know that, and it could be a good business. So for them, if you know.
Will, do you want to say something about your research and support for it?
Sure. So I guess a similar story in a way. I mean, I think that there are niche partners who are already interested. I think we probably have a job to do in terms of trying to convince other partners that there could be interest there. So that's something that we could perhaps think about as a community, perhaps a bit more. There's probably all sorts of applications and areas where we could try to gain interest. But like Joerg and Lorenzo, then but in terms of keywords in grant proposals, but I think that's more of an indictment of the grant proposal process than the specific science. So I think you probably have much better chance of getting funding in syntactic foams if you put machine learning or digital or security in front of the proposal. So there is money there, and I mean, in the UK we've seen a lot of investment in general advanced materials over the last sort of decade. So there's definitely space to move into in terms of whether it be syntactic foams in their own right, or perhaps the manufacturing of syntactic foams or related activities. So I think there is potential, but we probably could do more to sell the topic to other fields.
Yeah, so all of you mentioned about the applications and interest from industry being useful. Have you seen any large-scale applications of syntactic foams from your own experience collaborating with companies? And maybe we can start with Joerg about it, that you work with metallic foams, and we also have a question right now open that what kind of applications you've seen for metal foams or metallic syntactic foams, especially coming from industry?
Okay, metallic foams in general, especially the aluminum foam sandwiches, they are in production. It's not a large production, and we see that the companies, they are not growing very fast, but they exist. For syntactic metal foams, so far, I do not know about any industrial application. It's a pity because, especially when you think about the injection molding technique, it would be very, very easy to transfer this technology or the metal foam to this technology. In this case, the spheres are just one addition to the feedstock. So they don't have to change the machines. They don't have to change the process. They just add a little bit of a addition. So we have several companies in Germany which would be able to produce this material. But unfortunately, so far, no real application, at least as I know.
Okay, because in the US, I think the latest Navy ship, USS Zumwalt, had large-scale applications of syntactic foams in construction. And I've been hearing from companies about other large-scale applications in underwater or ship applications, even aerospace. But I don't see that much buzz in metal matrix syntactic foam area from the applications perspective yet. So we are always talking about potential applications, but not really something that's going to be in production soon.
Yeah.
So that's why my interest was there in asking you this question.
Yeah, we see, as I showed you, our institute is quite large, and we have a lot of polymer technology and surface technology. And the colleagues, they are working a lot with syntactic foams in shipyard industry, and so on. You find the glass spheres everywhere, but not in metals. So at least so far.
So Lorenzo, you already mentioned collaboration with CMT and other companies, but are there other applications that you have seen in the field for syntactic foams?
The largest application I saw is the one I mentioned with Intermarine, because they produced these large, they used the synthetic foams for the structure of these large ships, and they even had their own sub-company, let me say so, in close to Venice, where they produced their own thermoset materials. And it was quite impressive. Just the curing of this big structure was quite challenging.
Yeah.
And that's the largest thing I've seen.
Okay. Will, do you want to add something?
I think so. I mean, in terms of my direct engagement, it's mainly been in, similarly in sort of marine environments. But I mean, I know that, so we had quite a few people attend the workshop in some other diverse applications. So that, there's kind of transducer design was one in terms of impedance matching. And also, as you suggested, automotive, aerospace. I'm not sure, because I'm not at that end of the applications spectrum, but in terms of how much it's currently being used in those applications, you may know better than me, actually.
Okay. And since two of you are coming from modeling background, one question I had was, what kind of experimental data would help people who are working in modeling and simulation studies? Because quite a few people are interested in doing experimental work, but that needs to feed into something that can be useful for your work. So Will, can you start with that, and then we'll move to Lorenzo?
I mean, I think better characterization in general of materials, would be very good. I think what would be nice is if we could start to think about, what's possible in terms of materials design. So in terms of having a sort of constituent material palette, to build your materials from. So often I think the trend is to sort of take something that we have, stick it in a matrix and then see if it's got some interesting properties. So it would be quite nice if we could start to think almost the other way around and think to try to, optimize some kind of material property, and what type of microspheres do we need in order to render that property, whether it be, some distribution of sizes or mechanical properties, etc. So I think it's almost like a double-edged sword. You need to look at both ends of that sort of process. So Lorenzo, I know we discussed this some time back, actually.
Yes, I totally agree. Given that I think that the multi-particle unit cell models we developed so far are potentially quite accurate, and given that we couldn't match very well some experimental results, I draw the conclusion that we don't know yet the many features of the behavior of the single phases at that scale. Mostly for what concerns the strength at that scale. So I think we need also some statistics to be plugged into these models. But most of all, I guess for instance, if you take an epoxy resin, I guess the behavior at the scale of centimeters of plain epoxy resins may be quite different from the behavior of the same epoxy in a microstructure, where the curing may be different, and there can be an interface, that there can be interface issues. So I think the material characterization at that scale is very important, and I guess can be even quite difficult. I remember that once here in Brescia, we produced glass epoxy synthetic foams by sterilizing the balloons, and that changed quite a bit the behavior. Of course, mostly intention, but anyway, it was the proof that we really need a characterization, which is more difficult if the volume fraction increases, because the size of the thermoset becomes smaller, and unwanted voids may become more critical, and so on. So I think the experimental characterization would be really fundamental, and I don't know how much difficult. But.
So along the same lines, there is a question by Navjeet, and I was also interested in this, that in the homogenization problems, you don't really capture the nanoscale effects that come in. Mostly we are talking about microscale particles, and the model works really well. But if you had the same hollow particle at nanoscale, maybe 100 nanometers or below, what would be a good modeling scheme, and what would be the differences in properties that you expect at that level? And Will, I think you've been working a lot with the particle wall thickness characterization using your micro CT. Maybe you have better insight into how this size scale at nano level would play out into the modeling.
I mean, we haven't done anything in terms of the actual interface effects, but I know about modeling in terms of, if you capture the interface properties by some mechanism, that could be molecular modeling or atomistic modeling of, using molecular dynamics, then you can put that into models which capture the size dependence effects as your particles get smaller, of course. So, if you have a nanoscale interface with a nanoscale particle, then you will get size dependent effects as the nanoscale particle gets smaller, which then obviously, eliminated as the particle gets bigger. But I think, coupled to what Lorenzo said, I think there are some quite interesting problems where the volume fraction is so high that the particles are almost touching, and then you get the interface effects between particles. And those kind of effects in models are probably quite difficult to capture, I think. Okay.
Lorenzo, do you have any insight? Because I think the failure models would also be very different when you have nanoscale particles. And I think you've been working in crystal plasticity effects and modeling of metals in recent work. So how would these interact with maybe dislocations and grain boundaries and other features in metals if you have these nano hollow particles?
Sure. If you don't go down too much with the scale, you can still use continuum models, and in metal matrix synthetic forms, I would expect to have the smaller being stronger size effect, because the boundary layer where these locations pile up make the material stiffer and stronger. So if you have, in other words, if you have a big grain, the boundary layer doesn't play any role, because it is too small with respect to the size of the crystal where these locations can move. But if the grain becomes very small, the size of the pile up, where basically plastic strain goes to zero and become relevant for the region occupied by the metal, and so you may have this effect. Of course, if you go down with the size below, I don't know, below tens of nano, I don't think that continuum models are relevant, can be used anymore. So actually I would be very very happy to join these two fields of research of mine. But now I think that it will be quite time consuming just to try to put some strain gradient plasticity into one of those three-dimensional models. I think my PC would burn, but I don't know.
Yeah, we can stay with you for the next part of this question, because all of you mentioned machine learning in previous questions answer. So where do these machine learning models are finding their place among this whole micromechanics and physics-based models that are already available?
I haven't studied much of these machine learning techniques so far. I think if they are used to, I like them if they are used to identify material parameters of physics-based models.
Mm-hmm.
And but you know, if they are used as a black box, I'm not saying that they are not going to be useful, but I haven't just looked at that kind of technology so far, because you know, I prefer just to try to understand the physics by writing down some equations, physics-based equations that I can understand. So I'm afraid I'm not much helpful on this aspect.
Will, do you want to add something?
Yeah, I mean, I've got a healthy skepticism of machine learning, but only in the sense that I think everybody should have skepticism of anything that becomes a little bit trendy. I mean, I think that you know, there's a sort of misconception with things like machine learning that it can solve all your problems without having to think, and you know, it relies obviously on having lots of data. So where does that data come from? You need to get that data. So you either do the data by you know, doing experiments, which are obviously costly, or you do models. And so I think that is where there is some potential for development. So linking, and I think this is where a lot of people in the material science community are seeing some promise, is trying to link physics-driven modeling, like the ones that Lorenzo has been talking about today, to data and optimization. So, you know, the word optimization has been around for a long time, well before machine learning, and I think that, you know, we should think about that. I think there are potential wins there, especially for things like syntactic foams, where one of the major benefits is trying to couple something like, you know, thermal insulation with stiffness and high volume fraction. So you've got, you know, multiple things going on. You want to try to optimize all of those, and it may well be, so going back to my point earlier about, you know, having this kind of materials palette, it may well be that, you know, when you go through the kind of optimization procedure, it takes you to a different part of the parameter space than you may have expected, and that tells you that you might need a particle or an inclusion or a microsphere that you haven't yet thought of and isn't available. Mm-hmm. So you could go back and, you know, ask someone if they can try and make you one. But
that's, I think an excellent point. Yeah, excellent point. Yeah. Okay, I'll take a question about applications from attendees. So, Joerg, have you seen any biomedical applications or electric car applications for these syntactic foams specifically, but, you know, foams in general, because electric cars are very much sensitive to weight, and biomedical applications also are looking at these engineered structures at very low density, but having tailored mechanical properties?
Actually, the signals we get from the industry are different. They say for electric vehicles, weight is not so important.
Really? Okay.
Because they can, when braking the car, then they can use the energy again in comparison to a normal conventional engine. You can use the energy to load the battery again. Weight is not as important as they said a few years ago. Nevertheless, we see some applications for metal foams. There are several electric vehicles running in the streets with conventional aluminum foam. mostly aluminum foam sandwich, because you can combine the high stiffness, the low density, with an additional impact safety from below. So the company Pol in Germany, they produce syntactic, sorry, not syntactic, aluminum foam sandwiches for several electric vehicles. As I already said, for syntactic foams, no real application. We see some potential in damping materials as sound of the gears of electric drives might be interesting. Not only for cars, but also for bicycles and so on.
Okay. And we have another question about use in construction. And this is specific that can these foams be useful in construction applications, especially can they make a big impact on the developing world? Any comments from anybody on that? Because I see some work was coming out from University of Alabama here. A group is working on these structures with which are safer, but also at the same time, syntactic foams have low thermal conductivity. So, the climate control can be better in some of these structures. So I'm hoping that we'll cover more on this topic in the next panel discussion, which will feature experts from the US, mostly from the industry. But I just wanted to put it in front of this group also to ask that if you have seen any applications that can be relevant to developing countries, or maybe applications that can impact larger world.
So I saw the same, Nikhil. I saw the sort of, I think it within roofs actually for construction, tiles in roofs, I think, purely due to the conductivity and the potential for insulation. Okay.
Yeah, I think insulation is going to be a big application, especially because they are lightweight materials and they can be using the locally sourced material for quite a few of these compositions and applications. Okay. So the next question I have is, I think we can start with Joerg on this one, that you already mentioned 3D printing of syntactic foams. So what kind of 3D printing technologies do you see relevant to metal matrix syntactic foams? And what kind of applications where these technologies can be useful?
Okay, actually, I mentioned printing techniques for foams in general or porous structures. Some colleagues, they had a look into the printing of syntactic foams. We face a lot of difficulties there, I have to say, because when you think on metal powder and the hollow spheres, size is different mostly, and the density is very different. So we face a lot of problems with mixing and so on. But for producing composites by means of 3D printing, I think the filament fusion technique would be the best. So colleagues are using this here, for instance, for producing metal matrix composites, iron with tricalcium phosphate for implants, for instance. So it would not be so difficult to replace the tricalcium phosphate, for instance, by the hollow spheres. And for the feasibility, this I think is the best technique. Yeah.
Okay. Well, do you have any experience with 3D printing or any thoughts about 3D printing syntactic foams?
Not specifically for syntactic foams, no, I'm afraid not, no.
Okay. How about you, Lorenzo?
No, I've just seen some 3D printing in constructions, but so nowadays they have this impressive technology to do additive manufacturing for these walls, And so there are so many degrees of freedom to be optimized. I guess there might be room for syntactic foams as well, because we all know that they are light and they are very good in insulating, but I haven't seen any specific applications.
Okay, maybe you can talk a little bit more about the challenging problems in modeling and simulations that need to be solved in the future. Maybe highly deformable particles or hyperelastic matrix materials, because I see a lot of work going into flexible electronics and soft robotics in this area, which are large strain type materials. And I'm not sure if those problems are solved properly yet in the literature for syntactic foams.
Yeah, I think one of the things with me is that so if you go to hyperelastic constitutive models, the issue is that they phenomenological strain energy function type models don't even work particularly well for homogeneous materials. So you can get a good fit to tension or one mode of deformation, then as soon as you start to look at another mode of deformation, then the model is catastrophically bad. So I think there is a lot of work to do purely by virtue of the fact that you have to somehow build some kind of nonlinearity in the model such that it can accommodate these different modes of deformation. I mean, I guess that depends on the application. If you are only ever going to compress your material and that's the only thing you're interested in, then you might be happy to have a model that's good in that mode. But I think generally, this ability to couple microstructural effects to macroscopic effects is critical. If you want to have something like a strain energy function which you can feed into finite element methods, which is what people want for applications, then we're going to have to work harder, because I think that's quite a tricky thing to do.
So you showed some results on micro CT experiments from your group. So are you using in situ mechanical testing in micro CT also to get the full field strain during compression or tension, and maybe try to use that for some of the model validation or development of new models?
We haven't measured in situ strain as in around particles yet, but that is actually something that we're looking at in sort of different applications, actually, for kind of neutral inclusion type applications, where you're trying to reduce the stress around a particle associated with adding a coating. So that's something we are looking at, and we will try to image that strain field by introducing nanoparticles that we can correlate.
Lorenzo, what about you?
So my guess is that on the one hand, we have this, we put this effort to have these models with this detailed microstructure. And in principle, we could put whatever we want to describe the behavior of the phases. On the other hand, I totally agree with Will. The problem is that, as I said, first of all, the phase behavior is difficult to be known exactly at that scale. And if you are interested in strong nonlinearities, it is probably wise to focus on a specific application and just to understand the behavior and to try to optimize the material. And so perhaps it is so that there is, and this is a good thing for all of us who want to do research. There is a lot of work to do to put all together, because just in some cases just the single phase behavior is not well known at all, and so there is a lot of work to do, and this is good. But
What kind of particles and matrix materials have you been working on?
Different. Here at IFAM, I started with Tixocast, particle reinforced aluminium, and most of the other work was really related to the syntactic foams, I have to say. If you think it's also a kind of metal matrix composite. So it's hollow particles, actually. So those were the two fields I personally have been working in. The colleagues also worked with other composites.
Is it mostly aluminum matrix, and what kind of particles? Like glass particles, fly ash, or other ceramics also have been tried from your group?
In the metal field, not that much fibers. We did a few tests with carbon nanotubes. Most activities in the last few years were on biological or medical applications. As I already mentioned, for instance, composites of iron with tricalcium phosphate, bioresorbable implants. So there was some work done in our department in this. For conventional structural applications, the market in Germany for metal matrix composites is not that good. So we look for special applications like implants.
Okay. All right. We have only 4 minutes left, so I think if you can take a minute and share your closing comments, that would be great. Can we start with Lorenzo?
Yes, my closing comment should be that modeling syntactic forms is a lot of fun, so I recommend it. And you know, there are so many degrees of freedom that there is room for everyone to contribute. And so a lot of work has been done, but you know, there are so many possibilities, and both from the analytical point of view, and probably nowadays most of all from the computational point of view, that I recommend to try to do something to improve our knowledge on this field.
Yeah, but in times like this, when everybody wants to do simulation and get nice pictures, getting students who really want to do mathematics is difficult.
I can give our three-dimensional stuff to plug something in and see what happens.
Yeah, no, that's why I'm especially happy to see that William is in this group as a mathematician. And I hope he'll train a lot of students to be interested in syntactic forms and their problems. William, do you have any thoughts to share?
Yeah, I suppose following up from Lorenzo's comment, really, that I mean, I guess what I'd say is that interdisciplinarity is in this area is kind of more important than ever. I suppose, you know, the times when you can just you know, do a PhD and you're only interested in a model for this specific medium are, you know, not necessarily gone, but I think, you know, we have to look beyond the boundaries of where we are, and certainly, you know, that's what we've been trying to do in order to sort of reach out into different communities and build links to experimentalists and people with different techniques. Of course, that requires time, and we're all struggling with time at the moment, I think. But I think, you know, what you're doing here, Nikhil, Gary, is a fantastic thing because it connects people. And I think, you know, I've already had lots of ideas from just from what's been discussed today about how we could do things, and perhaps how we could collaborate as well to try and, you know, better the field and what we can contribute.
Thank you. Joerg?
Yeah, thank you also for the possibility to take part in this panel. And looking into the future, or at the moment, funding is not so good in this field, but we are still diligently working. I think it's a nice field for research, and we still have a lot of ideas. And of course, we are, as applied researcher, dreaming that we will find it someday in some car or some bicycle or so on. So we are working on this.
Thank you. So I want to thank all of you for taking the time out from your busy schedule and joining us for this panel. I think this dialogue has been very important because in last year, as you know, no conference has been organized, and Syntactic Foam conference was canceled from last year. We don't know when we will be able to meet physically and, you know, discuss our ideas. So this forum was organized with the view that other researchers and students can hear from you directly, ask questions, and get some ideas for their work. So thank you very much. I greatly appreciate it. From the past two panels, the YouTube links are in the chat. Feel free to look at the discussions. We will upload this recording also on YouTube and circulate the link to everybody who has registered for this panel.